All right. So basically, now we are going to look at into a new type of instrumental analysis. Before this, you have learned about spectroscopic instruments, which is atomic absorption, and then you have looked into the atomic emission. You have looked into the ICP, ICP-MS, okay? And then you have also looked into how to prep the sample for inorganic analytes. And then on the validation part, for the spectroscopic analysis lah. Alright, so basically whatever that we have learned before for spectroscopic instruments is usually for inorganic analytes, okay? So now for chromatographic method or for chromatographic instruments, it is for the analysis of organic analytes, okay? So before this, kalau kita when we looked at into the sample preparation for inorganic analytes, we have done, for example, dry ashing, and then we do digestion where we destroy all of the organic analytes. At that time, the organic analytes is called interferences lah, because at that time we want the inorganic analytes only. Okay, but now we are focusing on the organic analytes. Okay, all right. So what is chromatographic method actually? What is the principle of chromatographic method? Okay, so I believe that all of you have experienced some kind of chromatographic uh, principle before this. Okay, so basically, based on this first picture, what can you tell me about chromatography actually? Based on this picture only. Anyone care to apa? To just give your opinion on what is chromatography based on this first picture. Anyone? Muhammad Ainul Naim?
Saya Doktor.
Okay. Muhammad Ainul Naim. Okay, so how? Uh, Based on this first picture, what can you tell me about chromatography?
Uh, I don't have experience Doktor.
Ya ke tak ada experience?
Yes
Okay.
Doktor.
Alright. Okay,
Clueless
so
Doktor, clueless.
okay, clueless. Alright, no, never mind. Okay, so basically, this is just a apa? This is a piece of apa ni tissue paper, and then this is like ink. Okay, ink on a tissue paper. Where, for example, you look at this one, the second last one here. All right, so this ink initially is a pink color. Okay, when you drop it when you drop it onto the tissue paper, for some reason it separates from the pink color, and lastly it becomes a yellow color. So basically, this is what chromatography is all about. In a nutshell, it is a separation of your ink here. So now we know that in your ink, in your pink ink, it does not have the pink pigments. It also have the yellow pigments as well. Whereas this one, when you look at this one, you have a blue pigment here, but as it moves, initially you have a blue ink, but as time progress, it deviates into a blue, black, and then there is a yellow pigment as well inside the blue ink. All right. So now I want you to understand that chromatography. This is based on this simple chromatography. It is a separation of substances inside your sample. All right. So in this case, you say that, oh, my sample is a pink ink. It's a pink color ink. But little that you know, inside the pink color, there is also a yellow color inside it, yellow pigment inside it. All right. Based on that, Muhammad Ainul, faham?
Faham Doktor.
Faham. Okay, good. So basically, before this, we have looked into a spectrum. into a spectroscopy spectrum. So now we are going to look into a bila we learn about chromatography method, kita tak panggil spectrum dah. We call it chromatogram. Okay, it's just the same thing lah. Okay, so basically based on this chromatogram, okay, you've looked at into this chromatogram, this one at the apa yang kat bawah ni. You've looked at that, and then you saw that inside this sample, it has been separated into 1, 2, 3, 4, 5 components inside your sample. So now your sample, for example, for this one, it is a maybe a plant sample. Okay, so now inside the plant sample, you have rutin, you have quercetin, and then whatever that we have back here lah. Right, so basically inside your sample, it is not just your analyte, it also have a variation of analyte where it can be separated and identified as well as quantified at the end. All right, so with that in mind, so basically the chromatography lies inside the separation method. Now we are trying to learn on how can we separate these organic analytes so that we are able to identify each of the components as well as we are going to quantify each of the components. So that's how you apply chromatography inside your separation methods. Okay, so now, so apa-apa pun, we are going to look into the definition lah, right? So the definition, I believe that this is very important as what we have looked before. What is spectroscopy? Before this, we have learned about spectroscopy. So what is spectroscopy? So in this case, what is chromatography? Okay, chromatography comes from two Greek words. Okay, in this case, we call it chroma and then graphy. It comes as chromatography. All right. So the important definition of chromatography is that chromatography is the distribution, or we can call it partitioning, of analyte between a mobile phase and a stationary phase. This is very important. There are three words here. There are three keywords that is very important, which is the distribution of analyte, or we can call it partitioning of your analyte between a mobile phase and a stationary phase. Okay, now three things are important: the distribution, mobile phase, and stationary phase. Okay, because starting from here, you are going to hear a lot about the distribution. What is the mobile phase? What is the stationary phase? Okay, so distribution. What does it mean by distribution? Okay, uh, to make it simple, distribution ni adalah uh, whatever your analyte likes. Okay, when your analyte likes to be in more in the mobile phase, then it will be distributed more in the mobile phase. It will be partitioned more in the mobile phase. But if your analyte likes to be in the stationary phase, then it will distribute much more inside the stationary phase. It will partition more inside the stationary phase. So it depends on the behavior of your analyte. Okay, behavior tu bukanlah behavior semata-mata. It depends on the physical properties lah of the analyte. Okay, alright. So let's look at the basic principle of chromatography itself. Right now, we are going to look in depth lah on what does it mean by distributing, what does it mean by stationary phase, what does it mean by mobile phase. All right. So the sample molecules, in this case we call analytes, are physically separated by distributing themselves between two phases. Right. So now you just imagine in your sample there are two compounds. Okay. There are two compounds inside your sample. So these two compounds will behave differently. Okay, behave differently based on their interaction or based on their distribution between the stationary phase and the mobile phase. So due to this different behavior, different distribution would create some sort like a separation between them. Right? So initially inside your sample, it has been together lah inside your sample, but as it has been separated due to their different behavior, different distribution between the stationary phase and the mobile phase. Okay, up until that point, do you understand what is mean by distribution and how does it been separated?
Doctor.
Okay, good. All right. So now we are going to look at into what is stationary phase and what is mobile phase. Okay. Stationary phase, as what is shown here, it is a solid packed into a column. All right, it is a solid coating on the surface point is okay. And then wherever that we have looked later on, we can look into a different type of stationary phase, whether it can exist as a solid and also it can exist as a liquid, which is embedded onto a solid surface. Okay, what is a mobile phase? Mobile phase pula is the gas or a liquid or a supercritical fluid. Alright, let me make this much more simple kalau you want to imagine it. Okay, now based on this picture, right? Based on this picture, what is the stationary phase, do you think? Anyone? Nur El Ain?
Yes, doctor.
Okay, so based on this picture, can you guess what is the stationary phase?
The yellow one.
The yellow one or the pink one is your analyte.
Oh.
So, the stationary phase apa benda? Stationary phase tadi, when we look at here, the stationary phase is the solid packed into a column. Ataupun it is a liquid supported on a solid. Okay. Based on this picture, your stationary phase is the tissue itself. Okay. The stationary phase is the tissue where it moves. Okay. The mobile phase, later on we will look at into the mobile phase is the one that is carrying your analyte. Okay? Alright. I know that this is going to be a little bit apa macam tak faham sangat, but it's okay, we will look at into later on, in depth later on, but now when we look at stationary phase, okay, based on that picture, you straight away, okay, stationary phase is the tissue paper. Alright? The pink one or the yellow one is your analyte where it has been separated. Okay? Kan daripada the first drop of ink, which is the pink ink, that is your sample. But inside the ink, there are two analytes, which is the pink analyte, pink pigment, and then the yellow pigment, which is your second analyte lah. Alright? Okay. So now, why do we do chromatography actually? Why? So basically, when we do chromatography, it is to separate two or more compounds in a mixture based on the differences in the property of each of the individual. Right. This is what I mentioned before. Chromatography, the separation would depend on the differences in the property of the substances, or in this case of the analytes lah. So, what makes what makes it difference? So in terms of the polarity, in terms of solubility, ionic size, and the size of the analyte. So back to my example earlier, the two compounds, the two compounds inside your sample will have a separation because compound A is much more bigger than compound B. So that is different in size. So compound A might be eluted much more earlier than compound B, which is much more smaller size. Something like that. So difference in size, difference in ionic strength, different in polarity, and difference in solubility would create the separation. Because these differences properties would have an impact onto the apa tu onto the distribution of your analyte onto the mobile phase or onto the stationary phase. Right? Okay, so based on this picture, you can see that there is a mixture here. Okay, there is a bigger yellow yellow circle here. There is a red, which is much more smaller, and there is lagi kecil, which is the black circle. Then this is the inner mixture, and then we do separate it. So separation inside the mobile phase and also the stationary phase, and then end up we can have a separation of them, which we the bigger one, the medium one, the smaller one, and then towards the end we can analyze, identify, as well as purify and quantify them. Okay, all right. So this is an important apa orang kata important important theory that you need to know. Okay, light dissolve light. Okay, you need to remember that non-polar analytes would love a non-polar stationary phase, while a polar analytes would love a polar stationary phase. Okay, it based on the light dissolve light principle. Okay, so as you after this, I would like you to think that non-polar analyte would only be able to be separated in a non-polar stationary phase, while a polar analyte would be separated in a polar stationary phase. Okay, faham tak light dissolve light ni? Light dissolve light principle. Any question up until this point?
No, Doctor.
No. Okay, alright, thank you. Alright, so yeah, simple chromatography in life, so that's what I said. Okay, now maybe this much more better, this is clearer lah. Okay, so maybe kalau now you are at home, you can just try this. Okay, so you just take a marker ke or whatever, crayon, no crayon lah, marker lah, with ink. Okay, so you just place a dot onto the tissue paper, and then you place it into macam a glass where you fill it with water. Later on, the water will move upwards. Okay, the water will move upwards. This caused by what? Any guess? Ada guess tak?
Capillary effect.
Yes, capillary effect. That's good. So the water will move upwards the tissue paper by capillary effect, and then it will carry your ink upwards as well, kan? By capillary effect as well lah. Alright. So now this is the chromatography. The water is your mobile phase, while your stationary phase is the tissue paper. So the mobile phase, as what I've mentioned before, mobile phase ni it moves. The stationary phase, it stays there. So in this case, the stationary phase is your tissue paper where it's just stay there. Okay, it doesn't move up and down. The water is the only thing that is moving up and down, carrying your analyte, which is in this case your sample lah, your ink here, upwards by capillary action, right? So this movement of mobile phase together with your ink create a separation. Okay, create a separation where initially it is a pink color, but as it moves upward, it carrying just the yellow color. So yellow and pink here must have a different kind of size or a different kind of polarity or different kind of ionic strength based on this apa? Based on this polarity, solubility, ionic ionic strength and size. So based on these differences, this will create a separation where you can see that the pink one will just stay at the bottom while the yellow one moves with the mobile face upwards. Okay, this is the simplest chromatography lah. Okay, maybe later on you can try lah to see that what what are the pigments inside your ink. Whether, for example, for this yellow ink or this orange ink, maybe there is a there is a sorry yellow pula the orange pigment. There is a yellow pigment inside it as well. Okay, so all right. So this picture also shows the chromatography as well. This M&Ms. I believe that you initially this is a orange color M&Ms. All right. So you just put orange color M&Ms in the middle here, and then this is like a big tissue paper, and then you just have water where it moves upwards. So the little that you know that there is a blue color inside your orange M&Ms, or maybe this is a brown M&Ms initially. All right. Okay. All right. So that is how chromatography is inside your daily life lah. Okay. So there are 5 simple steps in chromatography, right? But it is not this simple lah. Okay, this is the 5 major parts in the 5 major steps in chromatography. First of all, is to introduce the sample. Okay, introduce a sample, and then this which is your sample needs to be containing the analyte. Okay, and then your analyte is going to be retained on the stationary phase. Retain here means that it have an interaction with your stationary phase. Okay, as your mobile phase bringing it upwards, the interaction of your analyte with your stationary phase would affect its separation. Okay, if your analyte have a higher interaction with your stationary phase, it will hard to be moved by the mobile phase. If your analyte has a low interaction lah with your stationary phase, then it will move much more easily with the mobile phase. Okay, that's in terms of retain lah. Kalau high interaction or high retention, then your analyte will spend more time inside your stationary phase rather than following mobile phase. But if your analyte is lowly retained by your stationary phase, or weakly retained lah, we can call it weakly retained by the stationary phase, then it will move according to the mobile phase. Right. The third step is the elution or stripping out the analyte. So basically, elution would happen when there is a separation. Alright. So elution ni, okay, for example, for this one, we look at this one. Okay. So you put your sample at the top here. You put your sample at the top here. So basically, this is your plant sample. Okay. Inside the plant sample, xanthophylls and chlorophylls would retain much more higher inside this stationary phase. So this is a silica stationary phase throughout. Okay. So your stationary phase here is a silica, this white thing, and then your mobile phase maybe some sort like maybe a solvent lah, methanol for example, right? So the methanol would be pumped throughout this column, throughout this tube, and it will elute here. It will come out here. Right. So now the job of your mobile phase is to bring all of your analytes, which is in this case there are 4 compounds inside your sample, through the stationary phase and elute out here and down here. Okay. So for example, at the top here, okay, you put the green sample lah. So just a green plant sample, right? So as it follows the mobile phase, as it follows the methanol, it would be separated into four types of compounds. So means that inside your sample there are four types of compound, which is xanthophylls and chlorophylls, which is at the first zone here, and then there is a beta carotene here at the second zone, and the third zone is the alpha carotene, right? So as it moves towards this stationary phase, okay, based on this, which one do you think has much more interaction with the stationary phase? Anyone care to answer? Which of the components ni yang memang highly retain lah, memang tak nak ikut mobile phase tu keluar? Don't want to follow the mobile phase out. Nur Sara Batrisha? Nur Sara Batrisha ada ke?
Ada doktor.
Okay, alright. So based on this, which component do you think that is highly retained by the stationary phase? Yang memang tak nak ikut stationary apa dia keluar kat ujung ni.
Apa tak nampak? Kento tu ke?
Yang mana yang atas ke yang bawah? Aku cakap yang atas bawah.
Atas.
Yang atas. Alright. So that is correct. So basically the on top here, the xanthophylls and chlorophylls have much more higher interaction with the stationary phase. So that's why it stays here on top. It takes more time to follow the mobile phase down. So which one has the less interaction with the mobile phase? Mobile phase, less interaction with the stationary phase, which is the alpha carotene. So alpha carotene have the weakest interaction with the stationary phase as it moves uh, according to the mobile phase lah, because that's why it's at the bottom. So based on this, alpha carotene will elute first, and then followed by beta carotene, and then it will follow by the xanthophylls and chlorophylls. So xanthophylls and chlorophyll will take much more longer time as compared to alpha carotene and beta carotene. Okay, understand? You guys understand on that matter?
Yes, doctor.
All right, good. Okay, and then the fourth step is the separation occurred, and then lastly you collect the chromatogram lah. Okay, so based on this, you can based on this, this is what we call column column chromatography lah. Okay, column chromatography, but you are using instruments which is have the same principle here. Okay, so later on we will see in terms of how to are you going to interpret chromatogram, right? All right, so basically this is the same as what I have mentioned before lah. Okay, so the solute has been introduced, which is your mixture has been introduced on top here, and will interact or retain differently lah, based on the physical properties of the uh, mixtures or your analytes, right? So elution is the process of washing components through the column by adding mobile phase, which is based on my example just now. Your mobile phase is methanol, right? So based on this, the purple one here have the most interaction with the stationary phase. Why? While the blue one here, the blue triangle, has the least interaction with the stationary phase. So that's why the the apa the green the blue compound here will elute first, followed by the green one and the purple one, purple or pink one, something like that. Okay, all right. So this is how, for example, later on when there is a question on explain the what is chromatogram is all about. So this is how you are going to explain it. Okay, right. because it is important for me to make sure that you understand the concept rather than you just read it. Okay, when you understand the concept, you are freely to explain it however that you can. Okay, with whatever uh, kind of explanation. All right, but it is important for you to have the keywords lah. So interaction with the stationary phase, the mobile phase, okay, and then the partition and distribution keywords, right? Okay. Okay. Now we are going to look at into the classification of the chromatographic separation. Okay, chromatographic process ni, chromatographic separation can be divided into 5 types. Okay, 5 types of chromatographic separation, which is 5 types of stationary phase lah. Alright. So the first one is absorption chromatography, and then partition chromatography, ion exchange chromatography, affinity chromatography, and gel permeation or size exclusion chromatography. Alright. Let's look into what is adsorption chromatography. Okay, adsorption chromatography, which is your apa? Later after this, you are going to learn about thin layer chromatography. Okay, thin layer chromatography is an example of adsorption chromatography. Right. So the solute and the solvent compete for the active sites on the solid absorbent. All right. So based on this figure, there are many active sites, okay, inside this absorbent. All right. The active sites of the stationary phase, which in this case, the stationary phase is the silanols of silica, interact with the functional groups of the compounds, which is represented by the red, by the red circle here. Right? So the interaction, the absorption chromatography would depend on the hydrogen bonds, van der Waals forces, which is attraction or repulsion, and then the hydrophobic interaction. So there are 3 types of interaction in absorption chromatography. Okay. So they are competing for the active sites on the stationary phase. All right. So as relative absorption of the mobile phase is increased by manipulating the eluent, the absorption of the solute is decreased, thus eluted. All right. So basically, in absorption chromatography, they are fighting for the active sites, and when you manipulate the eluent or manipulate the mobile phase, then you would create some sort like a much more better separation. Hence, it will elute it out. Okay. So, this is absorption chromatography, right? So now when we look at a partition chromatography, so basically this one is based on a thin film formed on a solid support by liquid stationary phase, right? So the solid are partitioned between 2 immiscible liquids, and the system is manipulated by changing the nature of the 2 liquids. So more or less have the same principle as absorption chromatography, where we can manipulate the liquids where it will create some sort like a separation. Okay, never mind. We will look in depth in each of the chromatography later on, right? So this is ion exchange. So by its name, the separation would depends on the affinity of the charged stationary phase and then the charged species, right? So the stationary phase here is not just silica, or it is not just fighting for active sites. It is just based on the charge of the stationary phase. So, for example, here you see that there are 2 cations here, which is fighting for the negative sides on the stationary phase, but maybe the the green one here have much more higher affinity as compared to the orange cation here. Right? So it depends on the affinity of the charged stationary phase, which is the blue one. This is charged stationary phase, and the charged species. right? All right, that is for ion chromatography. Okay, it goes by its name lah. It based on the ions. All right, size exclusion chromatography pula, it by its name as well. You can see that it is based on the size differences, right? So the stationary phase, in this for size exclusion chromatography, it contains porous material that have pores. All right, the stationary phase have pores where the pores would have some sort of like a size lah. So the smaller size will retain much more longer inside the pores, where the larger size which much will elutate much more faster because it has no interaction with the stationary phase, because the stationary phase now is they have pores which is based on the size. So kalau if your analyte, the analyte is much more bigger than the pore of the stationary phase, then it will not be having any interaction. Thus, it will elutate much more faster. All right. And then lastly is the affinity chromatography. Okay, affinity chromatography. This is separation which is based for the specific and reversible interaction between a solid molecule and a ligand. So usually this is done for proteins or enzyme, for the separation of proteins and for separation of enzymes. Okay. All right. So all of this chromatography punya chromatography punya classification, all of this is good for you to know each and one of them. Okay, to know the principle of each and one on each one of them, what kind of separation that they do have, all right, and what are the examples? How can the separation can be achieved? All right. Okay, up until this point, do you guys has any question? Okay, Arif said thumbs up. Okay. All right. So, can we take a 5-minute break before I continue on the chromatogram? On, yeah, chromatogram. Okay, ke? All right. So maybe we have a 5 minutes break. Okay, 11:45 we come back lah. Okay. Maybe I will just put on back the apa? The attendance. If anyone who has not apa sign in that, you can scan the apa the attendance form here, the attendance QR code. All right. So now it's 11:45. Okay. Sekejap. Okay. To chromatogram. Okay. Share. Okay. Can you see my screen? All right. Okay. Let's look if there is any question. Okay, Sachwin asks, yes, the test will be on Thursday and until chapter 6. Yes. All right, chapter 1 until chapter 6. Right? Okay. So, now we are going to look at what is chromatogram. Okay. Chromatogram is the output signal versus time, or the element volume, which is called a chromatogram. Before this, in spectroscopy, the spectrum, it is the intensity or the signal versus the wavelength. Kan? Inside your spectroscopy punya spectrum. Right? For chromatogram, it is the output signal, which is on the y-axis, and the time time of elution time. Okay? So analytes differ in their affinity for the stationary phase versus the mobile phase. Alright. So based on this chromatogram, okay, just this is a simple chromatogram. Okay. A, B, C lah from the left, yeah. A, B, C. Okay. So the time, okay, the A much more lower time as compared to C, which is much more higher time. Okay. Which one elute first? A, B, or C? Any guess? Sajwin? Ataupun anyone want to try to answer? Tak dengar sangat lah. Hello?
Doctor, is it A?
Alright. So, thank you, Go. That is correct. So, basically, A elute first. So, that's why the time is much more lower than C. So, when A elute first, does A have a strong interaction with stationary phase or a low interaction with the stationary phase?
Low, Doctor.
Low. All right, that's good. So my job here is done. All right. So basically, when you look at the chromatogram, you initially think that the first peak that has come out, which has the lowest time, which is in this case the shortest time lah. The shortest time is the thing that is elute first, means that it has the lowest interaction with your stationary phase because it just follow your mobile phase and it is eluted first, right? So it is a different situation with C. Okay, C eluted last, which means that C has the highest or has the higher interaction with stationary phase. It takes time to follow the mobile phase and eluted, which means that it is eluted last lah, right? Based on that, each analyte will exhibit different retention or migration, and elution patterns and mixture of analyte can be separated and quantified. So based on this, when you have a different kind of interaction, This is the separation actually. Okay, so we can inside the mixture, initially you have a mixture of A, B, and C. But when you do chromatography, you can create this, when you get this chromatogram, you know that A, B, C has been separated. Okay. But how do we know that A, B, C has been well separated? Okay, well separated here means that whether it has been separated individually. Okay, 1, A, B, and C. Okay, sometimes you might get A and B mixed together. If A and B mixed together, that means that it has not a good it have not a good separation lah. Okay, sometimes it will mix three of them, so means that your separation does not work. Okay, let's look into the characteristic of the chromatogram. Okay, so now this is your peak. Okay, this is your first peak, this is your second peak. Right. So let's look at the terminology lah. Right. So what when we say that what is T0 or what is TM? Okay. T0 or TM, we can call it as the void volume or the dead volume, which is the retention time of the unretained compound. Means that compound that will have not been have does not have any interaction with your stationary phase. So we can call it T0 or TM, okay, which is the void volume. Okay, so in this case, this is just a small peak here, which is we call that this is T0, right? TR1 or TR2, which is the retention times for the separated components. So TR1 is the from 0 here up until the first peak, which is the middle of the peak. But for TR2, which is the retention time 2, start at 0 up until the peak number 2 here, right? W1 and W2 is the width of the base peak of the component lah. So this is the width. Okay. Width here, the width under the curve here would have an effect on the concentration later on lah. Right? Okay. These are the terminologies, some of the terminologies that do you need to know. Okay. What is the dead, we can call it void volume lah, ataupun dead volume. Alright. So what is what is the retention time? What is the width? Okay. Alright. So retention time, now we are going to look at the definitions and some calculations lah. Okay, retention time. Retention time is the time elapsed between the injection of the sample and the emergence of the peak maximum. Alright. So now, when you look at this, when I say that here, which is start at 0, this is the time that you inject your sample in, that your sample has been put into the instrument. So up until when your first peak come out, what is the time taken from the time of injection up until the emergence of the first peak? That is your retention time number 1. Retention time number 2 is the same from the time of injection up until the time of emergence of the second peak. Right. The mobile phase hold up time, or T0 or TM, which is the time required for the injected solvent or any other unrelated compound to transverse the column, which is to elute from the column lah. Alright. So that is called T0 or TM. Right. So adjusted retention time. Adjusted retention time is the retention time with apostrophe here. Okay. T apostrophe R, which is the retention time minus the T0. So whatever calculations that you have after this, the real retention time is TR1 or TR2 minus the T0 or TM here. Alright? Okay. So that is called adjusted retention time. Is the difference between the analyte retention time and the column void volume. So this column void volume is something that is common. Alright. So you need to do your calculation based on the adjusted retention time. As what for example, before this we have looked into the as before this, when we do this calibration, you need to minus the blank signal, isn't it? So basically, you need to divide. You need to subtract the apa? You need to subtract the blank signal for you to get the correct signal. So this is more or less the same lah. The correct retention time, the time taken for your first peak to emerge from from your injection is need to be minus the E0. Okay? All right. Retention factor, or we can call it capacity factor, denoted as a small k, is a measure of how long a sample is retained with respect to the dead volume. So now we are giving a number for the sample that has been retained by the stationary phase. How long? What is the retention factor for the sample or for the analyte to be retained by your stationary phase? So retention time minus the dead time divided by the dead time. The dead volume lah. Dead volume, we can call it dead volume lah. Right? That is retention factor or capacity factor. What is the resolution pula? Resolution is how well of the two species separate from each other, which is the degree of separation. Okay, for this one, you can say that, okay, peak A to peak B is well separated. But what is the number? How can you say that it's well separated? You give me a number. So the number is based on this resolution. Okay, it is the formula here: 2 retention time 1 minus retention time 2 divide by the width of 1 plus the width of the second retention time lah. Okay. All right. So now we are going to look at, for example, for this one, the sample problem. Okay. Given the following data and the figure, calculate the resolution. Okay, so now we are going to look at the resolution between the first peak and the second peak. Okay. So to the retention time between the difference in retention time between the first peak and the second peak is 1.8. Okay, usually it is not this simple lah. Usually we will give you the retention time 1 and retention time 2 and you plot it into your calculation here lah. Okay, so for this sample problem, we have given you the differences. Okay, so 2 times 1.8 divide by the width number 1 plus the width number 2. So you got 2.1. So the resolution is 2.1. So when the resolution is more than 1.5, it means that they are well separated. If you got your resolution is less than 1.5, it means that it is not well separated. So we take the 1.5 value as the barrier between a well separated and the not well separated punya compounds lah. Okay. Up until this point, do you guys understand?
Yes, doctor.
Okay, all right. So now we are going to look at, okay, example of unresolved or bad separation. Okay, so for this one, the resolution is 0.5, which is not good. As I mentioned, we need to have 1.5. Okay, so this resolution is 0.75. You can see that maybe compound A and compound B, there are mixture inside the peak here, mixture of A and B. So your separation does not work, which is a bad separation. So you need to play around with the separation process. You need to play around with the stationary phase and you need to play around with the mobile phase so you can get a much more better separation, right? RS equal to 1. Okay, you can see more separation here, but it still is below 1.5. Okay, so the good one is 1.5. Okay, 100% separation. What if, okay, for example, you've got your separation about 10. Is it good or bad? Is it good or bad to have a resolution at 10? Anyone? Muhammad Hasanuddin said no idea ke? Sekejap saya tengok. No idea. Right? Too far maybe. Okay, yeah. That's good actually. All right? Okay. So basically, when you have the resolution at 10, so it shows that okay, it is well separated. Okay? But it is not efficient because we are playing with time. Okay? So, kan the formula is with time kan? So, the second retention time minus the first retention time, you got the differences. So, when you've got a resolution at 10, which means that the first peak and the second peak is too far away. When it is too far away, it shows that your separation is not efficient because we are playing with time. An efficient separation would create a good separation, which is more than 1.5, but it would be near to each other. Okay? Near to each other means that it saves more time lah, because your separation, you achieve 100% separation, but you would save time. Okay, we don't want a separation from compound A to compound B to become 10 minutes apart. Okay, compound A eluted at the first minute, while compound B eluted at the 25 minutes. So your separation is not good. Not good per se is that it is not efficient. So you need to play around with your mobile phase as well as your stationary phase to make sure that the peak is much more nearer to each other, but don't compromise the resolution. Okay. That's how you would think lah. Okay, that there are something good in terms of you have a good separation. Yes, it is well separated, but you still need to think about the efficiency of their separation. All right. Separation factor, or we can call it selectivity factor, denoted by the symbol alpha here. So this is a measure of how good a column can separate two substances by different chemical properties, which is for a given mobile phase. Okay, so basically, when you want to measure separation factor, it is by this formula lah. So the retention time of B minus the date time divided by the retention time of A minus the date time. Okay, so you've got about 1.4 here for this for this example lah. Okay, so the dead volume is at 1. The first peak A is at 3. The with 3. The second B here it may be at 3.8, something like that. Okay, so when you plug into the into this equation, okay, into this equation, then you've got your separation factor. Okay, improving the separation factor would give a much more stronger contribution in improving the resolution. Okay, right. So now after separation factor, there are a lot of formula here. Okay, but it is not that hard lah. Okay, it's not that hard to remember. Right. Now we are going to look at the column efficiency, or you can call it the theoretical number of plates, right? Usually column efficiency lah. So column efficiency is a measure of a broadening of the sample peak as it passes through the column. Okay, so how are we going to measure this column efficiency? Is by this formula. By this formula, n equal to 16 retention time divided by the width square, or when you are being given the width at half, so you divide everything at half lah, 5.54. The retention time, tr apostrophe here, which is what is tr apostrophe? Why this is tr and this is tr apostrophe? Apa beza tr here and tr apostrophe here? What are the differences?
Doctor, the TR apostrophe is the one that minus the dead volume.
Yes. Good. Good go. All right. So, yes, congratulations. You are, apa? You already know on the differences between the TR and TR apostrophe. Right. So when you have been given with the half value of the width of the peak at the half height, all right? Because sometimes you are being given the total width, or sometimes you are being given the width at half. So it depends on the width. So the width value that you've got lah. So you need to use a different kind of formula. All right? The higher the n value, the more efficient the separation is. All right? So usually n value, okay, for fractioning column, which is the one that we have looked before, yeah, the silica too, the column chromatography, the n value usually is about 5 to 1000. All right? But for HPLC, later on we will look into HPLC, which is the n value is about 50,000 to 200,000. So this is something for you to know only lah. Right? For GC, you will learn this with Dr. Amy. All right? So it's about 1,000 until 1 million n value. All right. I think this is the last. Okay. The last formula for you to know is the height equivalent to a theoretical plate or plate height. Right? Just simple call it plate height. Right? It compares the column efficiency, which is the n, the one that we have looked at before, with a different length. Okay, so column, uh, usually the column has its length can, because now we are playing with length and also with time. So the longer the length, it have much more higher retention time because it needs to travel through a much more longer column. But if, now we are going to look at into the plate height, which is the efficiency at the different length. Okay, now you need to know the length of the column. Okay, so H equivalent to L, which is the length, divided by N. The more efficient the column, the more the number of theoretical plates. Okay, the better the resolution and the smaller the H. That's how you apa? You connect all the dots lah. Alright. So the more efficient the column, we can say that okay, the column must have a high theoretical plates, which contributes to a better resolution, which contributes to the smaller plate height, which is smaller h. Alright. Because you divide by n kan. N ni if the value of n is much more is high, then you would have much more lower h lah. Okay. Alright. Let's look at the sample problem. Okay. An analyte with retention time of 407 seconds has a width at the base of 13 seconds on the column of 12.2 meter long. Sorry. So find the number of plates n and find the plate height, which is in this case h. So now, 16 times 407 second square divided by 13 because it gives the width at the base, not the half width here. The width at the base is at 13 second. Okay. If it has been given width at a half height, so you cannot use this you cannot use this formula lah. You need to use the 5.54. All right. So the n is 1.57 times 10 to the power of 4. So the h, which is the plate height, is the length, which is in this case 12.2 meter long, divide by n, and you've got 0.7 mm. Okay, so this is how you apply all of this formula lah. Okay. Okay, up until this point, do you guys understand? Do you guys can relate all of the formula, yeah? Or do you guys have any question? Ada soalan tak?
Tak ada, Doktor.
Tak ada. Okay, semua clear ya? Okay. Alright. Okay. Separation of mixtures would depend on the width of the solute peaks. Okay, so we want narrow peaks. Okay, we want narrow peak. We want the peak yang paling kurus lah kalau boleh. Right? We don't want the peak that is very broad. Okay, very broad means that there is something happens lah inside your separation. Alright, the spacing between the peaks this is resolution and selectivity. Okay, so we want a narrow peak because the narrow peak shows that it is efficient, and we want also the space between the peaks. We want a large spacing lah. Okay, but not too large. Okay, more or less 1.5 or 2.0 resolution. Okay. So the parameters which affect the resolution is the column efficiency, where more number of plates would give a narrower peaks and better resolution. And then we are looking at the capacity factor. If low K, which means that the analyte it's not be retained long enough for a good separation. Okay, because capacity factor we are going to look at into the interaction, on how long is the interaction for your analyte and your stationary phase. Right? Selectivity. So we are going to look at if the analytes are very similar, K1 equivalent to K2, then it will be difficult to separate. So this is how you look at all of these parameters. Okay, you look into each of it is just not just formula that you need to calculate, but you need to know on how to relate one to another. So this is what it means. Okay, it means. Alright? Alright. Effect of plate number number of plates, effect of n onto the alpha selectivity saya pun dah lupa dah. Yes, separation factor, selectivity factor, and onto the resolution. Okay, now we look at here. N, the number of plates is 250, but the resolution is 0.8. So you can see that, okay, the resolution is bad because it has not achieved 1.5. So poor resolution, bad calibration curve. Okay, so basically this is when we look at into the calibration curve lah. Alright. Now, when we look at the same number of plate, but the resolution has been increased to 1.8, which is more than 1.5. So it is a good resolution. So the same number of plates, but increased resolution. Okay. But how about if we increase the plate height, which is at 1100 with the resolution 1.8, you can see that the plate height, the increase in plate height would create some sort like a narrower peak. This peak, A and B, A lagi lah, but you can look at B. It has a good separation, but the peak is quite broad. As what we want to achieve is a narrow peak, which represented by the high number of plate here and a good resolution. So increased number of N, same resolution, better calibration curve. Alright? So this is how you correlate the effects of plate height and resolution. Okay? Okay. So this is the same thing lah. Okay, so this is the poor resolution, good resolution due to column efficiency. Alright, for this one is a good resolution as well, but you can see that the peak here is quite broad. Alright, so maybe the number of N is quite low. Alright. Okay, I think that's it for this for this part. Okay, do you have any question for the introduction of chromatography? Any question? No question. Okay. Maybe I can try to see this first. Okay. Sekejap ya. Okay. Alright. Can we continue for TLC, thin layer chromatography? This is just the simplest type of chromatography. Boleh ke continue? Sure, yeah. Alright. So, previously you have looked into the introduction of chromatography. You have learned what is chromatography. It's all about what are the formulas. Okay, what are the things that you need to know about chromatography. After this, we are going to look at TLC, and then maybe on Thursday we are going to look at apa? We are going to look at HPLC, and then right after you come back from your mid-sem break, you will learn about GC, if I'm not mistaken, gas chromatography with Dr. Amy Shazwani. Right? So let's look into thin layer chromatography. Right? Thin layer chromatography, basically it is done exactly as it says. All right? So it is a you can imagine that it is a thin layer apa? Thin layer, because thin layer chromatography is like a piece of paper actually. Okay, but not apa lembik macam paper tu, tak, dia very sturdy but it's very thin. Alright, so on top of it, on top of the aluminium that has been supported the stationary phase, so the stationary phase now, it is a uniform layer of silica. Alright, so you bayangkan, okay, this one, so the white one is the layer of silica or alumina, which is coated on a piece of metal or apa, maybe there is glass ke, or metal or rigid plastic as the stationary phase. So this uniform layer of silica would be on top of the glass, metal or rigid plastic. Okay, so the stationary phase is the silica itself, but it is embedded on top of the apa, on top of the glass, metal or rigid plastic lah. Okay, so the principle of separation by using thin layer chromatography can be partition chromatography, can be absorption chromatography, or also can be ion exchange chromatography, depending on the stationary phase that is being used. Right. Based on this, for example, when you do silica gel ataupun alumina, so this is the partition chromatography, right? If we have ion exchange chromatography, then then your stationary phase must be an ionic punya stationary phase lah. But in this case, it's just a silica. Okay, so this may be performed on analytical scale as a means of monitoring the progress of reaction. Okay, or on the preparative scale to purify some amount of compounds. Okay, but we will see on how do we use thin layer chromatography to do separation. Okay, so this is important. Okay, so this is how your thin layer chromatography works. It more or less the same as your experiment using apa tadi? Using the tissue paper and water. Okay, because it acts by the capillary action lah. Okay, the movement of the solution, the solvent upwards is by capillary action. Okay, let's look in part by part. Okay, different molecules are carried up the plate to a different distances due to the variable interaction with the absorbent material. Okay, so now you look here. Okay, the first dot here, the black dot, is your sample. Okay, it's your sample, and then you have your solvent here, which is down here is your mobile phase, and your stationary phase, this is the silica gel lah, the TLC plate which have the silica on top. Okay, you put your sample and then you look after 1 or 2 minutes, it starts to separate. It starts to separate where the black has become red, blue, and then black green here. Okay, and then as time goes by, as the capillary action moves upwards, where the mobile phase carrying up your analyte, it will separate into 4 types of dots here, which is the red, maybe this is orange, blue, and green. Okay, based on this, which dots have the least interaction with the silica gel stationary phase? Which color have the
Green.
least interaction? Yes, good. Siapa tadi nama apa? Siapa yang cakap tadi? Saya tak sempat tengok.
L-I.
Nur L Ain. Okay, that's good. So green has the least interaction with the silica gel. That's why it follows up the mobile phase. While I think this is the pink one, has the much more highest interaction, the higher interaction with the silica gel because it doesn't budge at all. It have maybe it has the highest interaction with the silica gel because it doesn't move. Okay, orange and blue moves. Okay, so this is how you create your separation based on the interaction of your analyte with the silica gel. Okay, so there are explanation here. For example, when silica is used as stationary phase, polar molecules, okay, which is for example, hydroxy group, tend to form hydrogen bonds with the silica. Okay, therefore it will not move as fast up as fast up the plate lah. All right. So silica gel. Now you need to know that silica gel is a polar compound. Okay. Silica gel is a polar compound. So it is for the separation of tadi. You remember the light dissolve light principle for a polar stationary phase. It is for, yes, good. It is the separation of polar compounds. So in this case, in these dots, which one is the most polar compound? Pink, orange, blue, or green? Which is the most polar compound?
Green.
Huh?
Green.
Green? Ya ke?
Red.
Pink. Pink kan yang bawah sekali tu. The lowest the bottom part is the bottom color is pink color lah. Kita put pink lah. Okay. So the pink color is the most polar compound here because it have a very high interaction with the silica gel, which is the polar stationary phase lah. So the green one is the non-polar compound because it moves as the mobile phase moves because it does not have any interaction with the silica gel, which is the polar compound. Okay, so when relatively non-polar molecules will have fewer interaction with the matrix and will tend to be more soluble in the mobile phase and then rise faster up with the solvent front. Okay, up until this point, you guys understand on how does TLC or thin layer chromatography works? Or is there any question? Is there any clarifications that you need on? Ada ke? Tak ada. Okay. Alright. Okay. It's okay. Alright. So this is usually what we do. Okay. So you place a dot onto the TLC and then you place it in your solvent so it will moves up. Right? Okay, so this is the same in terms of much more explanation lah on how are you going to do the TLC, right? The plate is placed, the TLC plate, this white strip is placed in a chamber where it's containing the small amount of solvent. All right, the solvent moves gradually moves up the plate via capillary action, carrying the substances, carrying the analyte along with at different rates lah. Okay, different rates. Why? Because the interaction. Why interaction? Because all of the analytes inside the sample have different chemical properties. Okay, and different interaction with the stationary phase. Okay, the components are absorbed onto the stationary phase. So the job of the mobile phase is to make sure that the the analytes move upwards. Okay, but at a different rate lah. Okay. And lastly, the separated components appear as a series of spots at a different location. So initially it begin at this straight line here. Okay. If you can see, there's a straight line that we mark with a pencil, right? So initially it begins here, and as time goes by, it moves upwards, right? So, okay, why I'm showing you this? Because there are a formula for you to calculate the movement, all right, from the movement from the place where you spot it up until the eluent front. Okay. So usually the spots are visualized directly if it is visible. You can see that if there is a color here, but if it is invisible, you can see it you can observe it under UV light, or maybe using a reagent to make them visible. In this case, usually we use anhydrine. Okay. All right. So TLC or T-layer chromatography usually has been used for qualitative analysis. Qualitative analysis is just for you to identify whether whether you punya reaction has finished, or whether there are some starting compounds. So it is just for qualitative analysis, right? So this is what I've mentioned before. Usually, if it is a non-colored solution, you can spray with a reagent, or you can observe it under UV light. All right, you can have a read on this. Okay, so now we are going to look at the retention factor. Retention factor, RF value, is the ratio of the distance that the substance travels to the distance that the solvent travels up the plate. Okay, it may be it's quite mouthful here, but RF value is the distance of component divided by the distance of the solvent front. Okay, so distance of component is the distance from the distance of the component is the distance of your first drop here. This is your sample up until the separated component, which is the blue one here. So the distance where you drop it, can initially we drop it onto the TLC. So this is the place where you drop it, and then as time goes by, it creates some sort of like a separation to become the blue and yellow one here. So the distance of component is the distance of the blue one here subtract the distance of the sample where you dot it initially. Okay, so this distance is dx, and then the distance of the solvent front is from the solvent up until the solvent front where the solvent ends. Kalau if this one, maybe you can see it much more clearer. All right. So the solvent front or the eluent front is the place where the solvent starts. So in this case, it starts at the line up until here. Can you see the differences? This is some sort of like a grayish color here, but this one is the white color. So where the line stop, where the solvent front stop, that is where you calculate the solvent front. Okay. So usually the best RF value is about 0.8 and more or less 0.4 to 0.8 lah. Okay. So that's how you measure the retention factor. Okay. So a good solvent system is one that moves all the components up. Okay. The solvent system, the mobile phase, is the one that moves all the component upwards. Okay, components of your mixture of the baseline, the one that you have created before, but does not put anything on the solvent front, right? So usually a good RF values is about 0.15 or 0.85. Here it says 0.4, but much more higher the ratio, maybe about around 0.8 ke 0.7 ke, it shows that your apa your separation is good lah, right? So these are all of the solvent that can apa that it's being usually used. So if it very polar solvent, methanol, okay, if it is a non-polar, usually it is a hexane, cyclohexane, right? So this is something for you to know, and you need to, because usually the question will give something like this lah. So the solvent is a hexane solvent. So you straight away know that the solvent is a non-polar solvent. The stationary phase is a silica stationary phase. So you straight away know that the stationary phase is polar. So this is for polar compounds, for the separation of polar compounds, right? All right. So the application of TLC, the application of thin layer chromatography is, as I mentioned before, is just mainly for qualitative analysis. All right, it's for you to determine the number of components. All right, so usually apa for TLC is for you to measure the completeness of a reaction. So in a reaction kan usually you place okay per reactant A plus reactant B will become reactant C. So how would you know reactant C has been the reaction has completed, so A and B is 100% being converted to C. Okay, so that's how you measure. So when you do TLC, you saw that, oh, there is no C yet. There is only A and B. So means that your reaction does not move or doesn't complete. For example, when you do it again after 1 or 2 hours, you see that there is compound A, compound B, and compound C. So it shows that your reaction is not finished yet. There are still reactants A and B which produce C. Okay, so that's how you use TLC lah to measure the number of components in the mixture, right? And then maybe to determine the identity of two substances, usually this is also for qualitative analysis. You have an unknown oil and you have your standard oil. Okay, so for example, you have this unknown oil, but it smells like lemon. Okay, but you place your your standard lemon oil onto the onto the TLC, and then when you do your separation, you see that at the end these two spots are aligned. So means that these two spots have the same RF value. So we can say that these two spots is the same thing. Okay, so you can say that your unknown is the lemon oil, that the standard that you have, right? And then we can see that in terms of biochemical analysis, in terms of the biochemical metabolites lah. Okay. Judge the purity of the synthesized compound industry. This is what I've mentioned before. Okay. When you saw that you have your reactant A, reactant B, and your product C, but then it shows that all of the reaction has not been finished yet because A and B has not been completely converted to C. Right? Okay. And then lastly is to indicate the extent of the progress of the chemical reaction. This is what I mentioned before. Okay. So that is all for TLC. Do you guys have any question for TLC? Any question? All right. Okay, so now it's 12:30. So I think that maybe we can maybe end our session for today. All right. So I will continue with HPLC on Thursday. So because on Thursday you will have your test. So Tengoklah kalau saya baik, saya buat apa? Saya buat async sahaja. I can record the lecture and you can spend the 1 hour to study for your test which is at night. Okay. So tengoklah kalau saya baik ke saya tak baik. Kalau tak saya buat sync session. It depends, okay? What do you want? Do you want async ke sync? Bukalah mic, cakaplah nak async.
Asynchronized, Doctor.
Okay, so you want async. Alright. So in that case, I will provide the lecture on the HPLC via async lecture lah. Right. So use the 1 hour to study for your test. Okay. So for your test, it's not going to be as simple as your quiz. Okay. So the test, Sashwin asked the format of the test. What do you mean by the format? Maybe you can open your mic and ask or clarify what do you mean by the format. How many questions? Okay, so it will be about 3 to 4 questions, which would carry about 50 marks. I have not finished creating the questions yet, but it would be about 50 marks lah, because your test is about 25 marks, 25%, but your test would accumulate to 50 marks. Okay, 3 to 4 questions. It will comprise of chapter 1 until chapter 6 last week. Okay? Alright. Is there any more question? Ada soalan lagi ke? Hello? Tak ada soalan. Alright. Okay. Alright. So for these two people, cepat scan the QR code. Alright. So whoever have yang dah scan and everything, then there is no more question, you can leave the meeting lah. Okay?
Thank you, Doctor.
Thank you.
Thank you, Doctor.
Thank you, Doctor.
Thank you, brother.
Thank you, Doctor.